To calculate the exact entropy of expanding periodic itineraries, the Symbolic-Branch program utilizes a specific operator-theoretic framework, the finite rank regeneration principle. This template requires 4 specific mathematical hypotheses to be satisfied. Theorem 4.29 proves that hypotheses 1, 3, and 4 are structural features of the entire expanding family. This identifies hypothesis 2 as the unresolved component of the template. This condition requires the spectral radius of the reduced return map operator, Q epsilon, to be strictly less than the dominant eigenvalue, lambda epsilon. If the spectral radius equals or exceeds the eigenvalue, the framework fails to provide a spectral gap, and the entropy formula remains uncertified. Empirical stress tests in Part 6 evaluated this spectral condition at near-critical exponent pairs. This plot tracks the spectral margin, delta, against the branch slope, lambda, as it approaches 1. We plot 2 near-critical pairs, 1219 and 5384. While neither fails, the data shows the spectral margin shrinking towards 0 as the slope approaches 1. Theorem 4.39 identifies the structural mechanism behind this trend. The continuous decrease of the margin indicates that there is no uniform spectral gap constant for the infinite family. The proof must instead verify the gap on a pointwise basis for each pair. We begin with the condition established in Theorem 4.38. The exponent pair A, P must be a best upper approximant of the ratio log 2 over log 3. This Diophantine property dictates the underlying geometry of the dynamical system. For these best upper pairs, the state space collapses to a single roll. N rolls equals exactly 1. In this single roll configuration, no piece beyond piece 1 can ever become active within the core. This restricts the active piece set for the system to only 0 and 1. By focusing on this single roll geometry, we can analyze the operator within a bounded environment, bypassing the complexities of the full multi-roll system. In this environment, piece 1 is the unique injection source for the reduced operator. This number line shows the A zone, which is the interval from 0 to the core boundary, hi0. Under the one-roll limit, all injected seeds from piece 1 map into this A zone. The injection ratio, rho, is the supremum of the seed divided by the boundary hi0. Because the seeds are trapped below that boundary, the injection ratio is strictly less than 1. This geometric constraint provides the necessary bound to solve the algebraic Lyapunov system. We can model the Lyapunov system as a balance between 2 algebraic terms. We parameterize the weights using A equals lambda to the W. The operator norm is determined by the age shift contribution versus the contribution from the single injection. We have 2 established facts. The dynamics are expanding, so lambda is greater than 1, and the injection ratio is less than 1. Since lambda is greater than rho, any positive power W preserves that inequality. This ensures the injection term remains subdominant to the age shift rate for any positive weight. This subdominance reduces the Lyapunov system to a single condition. A must be less than lambda. With the injection term mathematically trapped below the age shift rate, the spectral gap is confirmed for the one-roll case. The witness function, gamma of A, is defined as the maximum of these 2 competing terms. Because the injection is subdominant, this function simplifies to gamma of A equals A. By choosing any value for A in the interval between 1 and lambda, we obtain an explicit witness satisfying hypothesis 2. This leads to the equation for the spectral margin. Delta equals 1 minus the infimum of gamma over lambda. As A approaches 1, the margin converges to the ratio lambda minus 1 over lambda. This ratio matches the data from the stress tests. As the branch slope, lambda, approaches 1, the margin mechanically vanishes. The gap is present for every pair, but it is strictly pointwise. Theorem 4.39 proves that hypothesis 2 holds for every individual best upper pair. Combined with the general results for the other 3 hypotheses, the finite rank regeneration template is resolved for this specific arithmetic subset. This applies unconditionally to the infinite subfamily of best upper approximates. The Symbolic-Branch program links Diophantine arithmetic conditions to the existence of a proven spectral gap.